Okay, just let me start the next topic. That is, we need to understand about the LTE frame structure. Okay, so again and again, I don't want to repeat what type of multiple access technique is used in case of LTE for downlink and uplink. I hope. Is it possible to say, Aditya Datta, what is the type of multiple access used for uplink and what is the type of multiple access used for downlink? Aditya Datta. Hope Datta is there. Aditya Datta. Yes, Aditya Datta, I'm asking. Hello. Hello, Aditya Datta. No. Yes, what about Dharma? Dharma. Dharma also not ready to speak. Hmm? Yes, I'm asking Dharma. I think what Chandan Nayak has joined. Hmm? Okay. So as I said, OFDMA is what that is orthogonal frequency division multiple access is the technique used in the downlink, and a single carrier frequency division multiple access is the multiple access technique used in the uplink. Okay, in case of LTE, the people should understand this because already I discussed this several times. So I expected people to answer. Okay. So what I said, OFDMA is the type of multiple access technique used in the downlink, and SCFDMA. That is what is that? That is a single carrier frequency division multiple access, which is used in the uplink. And also, I have discussed why for uplink SCFDMA is preferred and why OFDMA is preferred for downlink, right? As I said, this OFDMA have more peak to average power ratio. So with that PAPR, high PAPR, what happens? It demands the high cost power amplifier. So with that, the cost of the handset will go high, right? So and even it consumes more power also. So to avoid that and to be more cost efficient, so SCFDMA has been preferred for uplink, whereas this SCFDMA can provide better energy and as well as cost efficiency for the with respect to the battery is concerned. Okay, fine. So that is one thing to understand what is the type of multiple access used in downlink and uplink. And second thing is, as I said, the LTE uses sub carriers, okay, which are of what frequency? 15 kilohertz apart. Okay, means the given bandwidth is divided into the subcarriers. That subcarrier spacing is of 15 kilohertz. Okay, so means as I said, this LTE supports scalable bandwidth, that is 1.4 megahertz, 3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, and 20 megahertz. Okay, so you have to find out how many subcarriers will exist with 1.4 megahertz of bandwidth, or 3 megahertz of bandwidth, or 5 megahertz, or 10 megahertz, or 20 megahertz, right? And in addition to that, there will be some amount of guard also, which will be of around 10%. Okay, means if I say 20 megahertz is the bandwidth, in that 10% is used as a guard band. Okay, so 10% of 20 megahertz will be how much? It will be of around 2 megahertz is used as a guard band, and another 18 megahertz is used for transferring the information. Okay, so with that, what I can say is here the value of FFT, right? The maximum value of FFT allowed is 2048. So this is the size of FFT, and how do we calculate that symbol duration is this 1 by 15,000. That is what subcarrier spacing, okay, 15K into the value of FFT. So that is 2048. So 1 by 15,000 into 2048 will give you the symbol duration. Okay, so it comes to this much, 1 by 30. How much it will be? 3 plus 3, 6 days, right? So just read that. So many seconds it will be. Okay, so here the downlink and uplinks are organized into radio frames, and the duration of that will be of 10 milliseconds. So that corresponds to so many. That is how much it is? 2 plus 2, 4, right? Means 3,72,7,200 into TS it is. You don't have to worry about this number. Just take it. The duration of the radio frame is 10 milliseconds. Okay. So what I wanted to highlight with this slide is the subcarrier spacing, which is 15 kilohertz, maximum FFT size, which is of 2048, and how do we calculate the basic time unit? That is TS is equal to 1 by 15,000 into 2048. That will give you the symbol duration. Okay, and I said that the radio frame duration will be of 10 milliseconds. And in addition to that, I said what is the type of multiple access technique used in downlink and uplink. Okay, fine. I think somebody's microphone is on. I think Vishnu, you can mute. Vishnu. Okay, it is creating disturbance. Yes, Vishnu. I think Vishnu's son only. Vishnu, are they ready? Hello. Over there. Yes, Vishnu. Hello. I don't know where the people will be. They don't talk also. Hello, class ನಡೀತಾ ಇದೆಯಾ? Okay. Yes, as I was telling, this LTE uses two types of duplexing techniques. That is, one is TDD, that is known as time division duplexing, and second one is FDD, that is frequency division duplexing. Okay, so in case of TDD, I think this fellow is not here. Yes, still Vishnu. Yes, Vishnu, are them ready? Okay, fine. Okay, so what I said, in case of TDD, the uplink and downlink transmission happens on the same frequency, but at different times. Okay, that is why it is called time division duplexing. In case of FDD, that is a frequency division duplexing, uplink and downlink will happen at a different frequency band. Okay, that is what you are supposed to understand. Okay, means uplink will be of one frequency band and downlink will be of another frequency band. But in case of TDD, what I said, both uplink and downlink will be on the same frequency band, but at different times. Okay. Then the next thing what you need to understand is, as I said, it uses two types of cyclic prefixes. One is the normal CP, that is normal cyclic prefix, and the duration of that will be this one 144 into TS, which will be equal to what? 4.7 microseconds. And second one is extended CP. In that case, it is 512 into TS. So I said the value of TS in the previous slide. I think why this fellow? Yes, Vishnu. Cannot remove also. Hello. Where he has gone, I don't know. Why don't understand? Hmm? Okay. Yes, Vishnu unmute. Yes, Vishnuvardhan Reddy. What this fellow is. Yes, somebody can call him, na? Okay, so as I was telling, why this fellow is not neither. Yes, Vishnuvardhan Reddy. And unmute also. Okay, so as I said, LTE uses two cyclic prefixes. One is the normal cyclic prefix, and second one is the extended cyclic prefix. So, in case of normal cyclic prefix, it will be what? 144 into TS. Okay, so I said the TS will be what in the previous slide I said what is its value, so it will come to 4.7 microseconds is the duration of the normal cyclic prefix, and the extended cyclic prefix will be 512 into TS, which will be equal to 16.7 microseconds. Okay. Yeah, so let me, I think you can just have a look how the spectrum has been allocated in FDD and TDD. The first case is FDD, that is frequency division duplexing. Now, as I said, for uplink, the separate band is used, and for downlink, the separate band is used. Okay, U1, U2, U3, U4. This is the uplink for each particular user. Similarly, D1, D2, D3, D4 is the downlink band, frequency band for user 1, user 2, user 3, user 4. So between this uplink and downlink, there will be a guard band. Okay. And in case of TDD, what I said, both uplink and downlink will happen, okay, on the same frequency band, but it will be at different timings. Okay, that is what the TDD is. Okay, so let us see the first FDD frame structure. Okay, even in this two types is there, type 1 and type 2. So type 1 is with the normal cyclic prefix and type 2 with the extended cyclic prefix. Okay, so here there are three different time units to understand. First one is the slot. Okay, so the duration of the slot will be equal to this one 15,360 into TS. That will be around 0.5 milliseconds you'll get. Okay, then subframe. Okay, as I said, the two consecutive slots is known as the subframe, and one slot duration is 0.5 milliseconds. So one subframe duration will be of 1 milliseconds. Okay, fine. Like that, so there will be 20 slots. Okay, 20 slots, and there will be 10 subframes. That will be equal to one radio frame, which is equal to 10 milliseconds. Okay. Yeah. So in case of type 1, okay, the normal cyclic prefix allows 7 OFDM symbols per slot. So this is important. And you need to understand how many OFDM symbols used in the normal cyclic prefix and how many OFDM symbols allowed in extended cyclic prefix. Okay, in case of normal cyclic prefix, it allows 7 OFDM symbols per slot. In case of extended cyclic prefix, it allows only 6 OFDM symbols. So by using the use of this extended cyclic prefix, okay, extended cyclic prefix results in this much of reduction in the throughput. Okay, but it provides a better compensation for the multipath fading. So this is how the structure of FDD frame structure of type 1. Okay, with both normal cyclic prefix and as well as extended cyclic prefix. Just have a look. So this is the duration of the cyclic prefix, right? And as I said, the OFDM symbol duration will be what? 66.7 microseconds. Okay, this into this plus the normal cyclic prefix duration. I think around it is how much it is 4.5 something I said, right? Yeah, 4.7 microseconds. If we add that, what we will get? 66 plus 7 plus 4.7. So it will be around 71 microseconds total, right? But to say OFDM symbol duration will be of 66.7 microseconds. So here to say one slot will have how many OFDM symbols I said? Yes, is it possible to see, say how many? Looking at this diagram, so it is 0 to 6 means 7 OFDM symbols. Okay, so 7 OFDM symbols will be equal to one slot. Okay, similarly for the extended cyclic prefix, right? So there will be 6 OFDM symbols in one slot, and the duration of the cyclic prefix is more than the normal cyclic prefix. Okay, here it is around 16 point something I said now. Yeah, 16.7 microseconds in case of extended cyclic prefix. In case of normal cyclic prefix, it is 4.7 microseconds. Fine. And already I said the 20 slots will be equal to one radio frame, right? And then the 2 time slots is equal to one subframe. Okay, so the duration of one slot is 0.5 millisecond, and the duration of one subframe will be 1 millisecond. So like that, there will be 10 subframes, and what we say the duration of one radio frame is 10 milliseconds. So it's simple to understand and write also. Okay. Yeah. So next one is the type 2, which is a TDM frame structure, what we say. Here also, the length of the radio frame is again 10 milliseconds only, but it includes some special subframes. Okay, this TDD frame structure type 2 we say. Here also the frame duration is 10 milliseconds only, but what is added here? It adds some special subframes for switching from downlink to uplink. Okay, so that special subframe is known as this downlink pilot time slot. So it is denoted as DWPTS. Okay, this is what download or not download. So downlink pilot time slot. Okay, downlink pilot time slot. So the downlink subframe of 3 to 12 OFDM symbols will be occupied by this downlink pilot time slot. Similarly, the uplink pilot time slot will be there. That is denoted by UP. That is uplink pilot time slot. Okay. So this will be having 1 or 2 OFDM symbols. Okay. This is for sounding reference signals or for random access preambles. So these are the special subframes which are added in the TDD frame structure, so which is not there in the FDD frame structure. So this is what the difference is. And then the guard period, you all know what is that guard period, right? I think, yeah. So this is how the TDD frame structure looks like. So 0 to 4 means 5 subframes. Here it is shown, right? One half frame, so which is equal to 5 milliseconds. In that 5 subframes, right? So I said there will be one a special subframe. So this is a subframe. In that everything is same. It will have 2 time slots. Each time slot duration is 0.5 millisecond. So total one subframe will be 1 millisecond. But what is that special subframe? I said no, downlink pilot slot, then guard period, then uplink pilot time slot. So that is what is there in one subframe. So this will be occupying one subframe. Okay, so this is the difference. So, and even I said why it is required also, right? Why the special subframe is required. So that is required for switching from downlink to uplink. Okay, is that fine? So downlink pilot time slot will have 3 to 12 waveform symbols, and uplink pilot time slot will have 1 or 2 waveform symbols. See one subframe. I hope you will be able to understand. One subframe will be having 2 time slot, right? I said one time slot will have 7 waveform symbols. Okay, means 2 time slots means for normal cyclic prefix it will be of 14 waveform symbols. So out of 14 waveform symbols, 3 to 12 will be of what? Minimum is 3, maximum is 12 waveform symbols is used for downlink pilot time slot, and 1 or 2 is used for uplink pilot time slot. So if they are using 1, then here 12 plus 1, 13 will be there. So one more time slot is used as a guard period. So which is shown between this downlink pilot time slot and the uplink pilot time slot. Hope this point is clear. So let me go to the next thing. Yes, this also already I said how this time frequency grid looks like, right? So as I said, the 6 or 7 waveform symbols will be there per time slot. So 6 will be there for extended CP, and 7 waveform symbols will be for normal cyclic prefix. And I said the sub carrier will be of 15 kilohertz. Okay, this also point I stressed upon what I said. 10% of the bandwidth will be used as a guard band for the channel bandwidth of 3 megahertz and above. Okay, and even this structure was known to you already. Okay, how the time frequency grid looks like, and what is the resource element, what is that resource block, right, and how that is related to time slot and subframe and the radio frame. Okay, hope able to get this point. So this is a resource element, means one symbol, one subcarrier frequency is a resource element. Then either 7 waveform symbols depending upon whether it is normal CP or extended CP. So if I consider normal CP, 7 OFDM symbols, then 12 subcarriers. That is 12 into 7 will be 84 resource elements leads to one resource block. Okay, so like that we allocate the resources to the users. Fine, I think, yeah. So as I said, to say what is resource block, it will have 12 subcarriers and 6 or 7 OFDM symbols. That depends upon the whether it is normal CP or extended CP. Right? For normal CP it is 7 OFDM symbols, I said. For extended CP it is 6 OFDM symbols. With that, we can say how many resource elements will be there. So if I take 6 OFDM symbols, then 12 subcarriers. 12 into 6, 72. 72 resource elements will be there in one resource block. So if it is 7, so 12 sevens are 84. So there will be 84 resource elements in the resource block. Okay, and another thing is for uplink, there will be continuous frequencies. Means continuous frequencies must be used for the 12 subcarriers. So that we call as PRB, that is a physical resource block. Okay. And for downlink, the frequencies need not be contiguous. So that we call it as a virtual resource block. I think these two are the catchy point you need to understand. What I said, for uplink, we need to have the contiguous frequencies. Okay, for all the 12 subcarriers. That we call it as a PRB, that is physical resource block. But for the downlink, frequencies need not be contiguous. So that we call it as a virtual resource block, that is VRB. Okay, so I think these two terms are important when we are discussing about the resource allocation in LTE. Okay, that is why you try to understand. So PRB means we need to have all 12 subcarriers in continuous. Especially it is used for uplink. Okay, for downlink, the frequencies need not be contiguous. Hence, that we call it as a virtual resource block. Yeah. Yeah, this is all about support from MIMO technique. So in LTE, can support 4x4, that is 4 antennas at the transmitter side and 4 antennas at the receiver side. LTE advanced can support 8x8, 8 cross 8 we say. Okay, and so ENB will be assigning the resource blocks with the channel dependent scheduling. So I already discussed what is that channel dependent scheduling. I hope we will be able to recall that what it is. Okay, so because we use multi-user diversity, so that can exploit to increase the bandwidth usage efficiency, and as well as it can assign resource blocks for user equipment with favorable qualities on certain time slots and subcarriers. And it can also include fairness considerations, understanding of user equipment locations, typical channel conditions, and as well as the quality of service priorities. So, yeah. So with respect to release date, I'm talking as of now, I think it is release 17. Okay, it is an old data. So release 8 supports up to 4x4 MIMO. Okay, so the E node B, whatever we say, uses the physical downlink control channel to communicate. Okay, PDCCH is the channel used by the E node B to communicate with the user equipment. So it will be allocating the resource blocks and as well as the timing advances for synchronization. So we'll understand this, what is the timing advance between uplink and downlink. Okay, how many slots difference will be there so that there will be no interference, and I'll see later on. Okay, and as I said, it uses two types of convolutional codes, right, with rate 1/3, and these are the different types of modulation techniques which can be adopted for the based on the channel conditions. QPSK 16 QAM and as well as 64 QAM. And yeah, with respect to this physical transmission of these resource blocks, so the user equipment will be determining what is the channel quality index. Okay, that is CQI, channel quality indicator. So that CQI index that will provide the highest throughput while maintaining at most 10% block error rate. Okay, so here for different values of CQI index, it is given what type of modulation is used and what is the code rate, okay, and what is the efficiency. Just have a look. I think if I use with the CQI index of 15, the type of modulation is 64 QAM. So with that, the efficiency will be of 5.5547%. Okay. So if you use QPSK, just understand what is the efficiency. It is 0.15 only. Okay. And if you use 16 QAM, okay, with a CQA index of 7, with that the efficiency will be of 1.4766. So you don't have to worry about this table, just you should have an idea. Okay, so depending upon the value of a channel quality indicator index, it will be selecting the type of modulation technique. Based on that, we will be able to achieve the desired efficiency. Means it will be giving this type of efficiency. Okay. So now let us try to understand about this synchronization signals. Okay, in the morning, what I said, the synchronization signals are used for synchronization, right? So let me say this: both the FDD and as well as the TDD versions of LTE uses the synchronization signals in both in the downlink direction. Okay. Both the FDD and TDD versions of LTE uses synchronization signals in the downlink direction. So these synchronization signals are used to facilitate the cell search procedure. Cell search procedure is there. We'll discuss maybe in the upcoming slides. So cell search procedure means what? So when you make a call, it has to find out, see, so many cells will be there, right? So that particular called party is staying in which, or there in which cell. Okay, that is what the cell search procedure. So the synchronization signals will be able to facilitate that. Okay, and also the synchronization signals are able to provide the time and frequency synchronization between the user equipment and as well as E node B. And as said, it will also be able to obtain the cell ID. Okay, so let me see what is a cell ID and all. I think in the next slide it is there. Okay, so, and in addition to that, these synchronization signals are broadcasted within every 10 milliseconds radio frame. Means in every frame, the synchronization signal will be transmitted. Okay, so the user equipment uses the synchronization signals to achieve the radio frame, okay, subframe, slot, and as well as the symbol synchronization in the time domain. So that is why I highlighted with this. So it is very important, what I can say. User equipment uses the synchronization signals to achieve radio frame. I said no, radio frame duration is 10 milliseconds. Okay, so to achieve that radio frame, even subframe is of what? 1 millisecond. Then slot is of 0.5 millisecond, and symbol synchronization. Okay, you know what is the symbol duration, which is including cyclic prefix, it will be 71 microseconds. So to achieve the synchronization of all these things, the synchronization signals are required. And it is also means the synchronization signal will also be able to identify the center of the channel bandwidth in the frequency domain. Okay, so in the time domain, what it does, in the frequency domain, what it does, I said. In the time domain, it is possible to achieve the radio frame, subframe, slot, and symbol synchronization. In frequency domain, it is possible to identify the center of the channel bandwidth. Okay, and I said it is also possible to deduce the physical layer cell identity, so which we call as PCI. I will tell what is that PCI. Okay, Miss physical cell physical layer cell identity. Fine. So detecting that a synchronization signal is a prerequisite to measuring the cell specific reference signals and as well as decoding the master information block, that is MIB, on the physical broadcast channel. Okay, so that is why I said now in the upcoming slides I will be using the terms which I said in the morning class: reference signals, that is user equipment cell specific reference signals. So I should be able to understand that what it is. So let me now tell about the physical layer cell ID. So I was telling in the previous slide. So synchronization signals are able to reduce the physical layer cell identity. So what is that? So we have a total 504 unique physical layer cell IDs. Okay. Total how many? 504 unique physical layer cell IDs. And those 504 unique physical layer cell IDs are grouped into 168 physical layer cell ID groups. Okay, so this 504 unique physical cell layer IDs are there. Okay, these 504 unique physical layer cell IDs are grouped into what I said, 168 physical layer cell ID groups. Okay, so then how do we calculate that physical layer cell ID? Okay, so this is what the formula we use to calculate the physical layer cell ID. So n to the power of cell ID, right? So the physical layer cell ID, which is equal to two terms are there. One, 3 times n to the power of 1. This is first ID and this is second ID. So first one, okay, this one will be varying from 0 to 167. Okay, physical layer cell ID group. N to the power of 1 of ID. This value can vary from 0 to 167, means 168 physical layer cell ID groups are there. So that into 3, if I do 168 into 3, you will get this value 504 unique physical layer cell IDs you will get. Okay. And I said these are the 168 physical layer cell ID groups are there. Okay, that has been grouped into 3 things. So that is why the second term is there, N2 ID 012. That represents the physical layer ID within the cell ID group. Okay, I said now 168 physical layer cell ID groups are there. In that, again with the second term, this represents what? The physical layer ID within the cell ID group. So you will get the clarity. What is this physical layer cell ID? All these things with that software, whatever I said. Okay, bullets.com, LTE-bullet.com. So you will be able to understand how to select that physical layer cell ID, how to calculate this one, and synchronization signals and all. Okay. Okay, fine. So each cell will be assigned a unique physical layer cell ID. Means, as I said, no, there will be 504 unique physical layer cell IDs, right? So each cell will be assigned one unique physical layer cell ID. So in this thing, as I said, there will be 2 types of synchronization signals, because these synchronization signals only will be able to deduce the physical layer cell ID. That is why I'm going to discuss about this. That is what primary synchronization signal, and second one is secondary synchronization signal. So let me say what is this PSS. So primary synchronization signals will identify the symbol timing and the cell ID index. Okay, so PSS will be identifying what? Symbol timing and as well as cell ID index. That is the second term of whatever the expression I wrote for physical layer cell ID. So that is PSS. The SS, that is the secondary synchronization signals, okay, are used for detecting the cell ID group index. Okay, that is the first term of the expression, and as well as the frame timing. Hope we're able to understand. No? So you will get a clarity about this calculation maybe when I show with the other slides. So as of now, you just try to understand. There will be 504 unique physical layer cell IDs. Okay, and they are grouped into what 168 physical layer cell ID groups. Right? So how do I define the physical layer cell ID? This is what the expression is. I said this varies from 0 to 167. With that, I said 168. 168 into 3 will get the 504 as a value. Okay, fine. So then I said the PSS is used to identify the symbol timing and as well as cell ID index. And triple S, that is a secondary synchronization signals, is used for detecting the cell ID group index and as well as the frame timing. So the synchronization signals are designed in such a way that they will be able to make the cell search procedure fast and of low complexity. Right? So, okay. So I was telling about primary synchronization signal. Huh? So how that sequence is generated. Okay. So the sequence used for the primary synchronization signal is what means the PSS is generated from the frequency domain Z of 2 sequence. Have you heard about this one? Any time about the Z of 2 sequence? So like pseudo-noise sequence, I hope you might have remembered. Pseudo-noise sequence, have you remembered pseudo-noise sequence? Yes, my dear students, I keep talking from my end, so I don't know all what people are doing. Yes, now Vishnu has, I think, he is muted. Okay. Yes, are you aware of pseudo-noise sequence? I'm asking. Hello, people are there with me? Don't know. Nobody is talking. Yes, my dear students, all are busy with your study or what? Hello? Hello? ಯಾರಿಲ್ಲ ಅನ್ಸುತ್ತೆ. Is it so? Yes, Akshata.
Yes, sir.
ಏನು ಕೇಳಿಸ್ಕೊಳ್ತಾ ಇದ್ದೀರಾ ಲೆಕ್ಚರ್?
Yes, sir.
Are you able to understand what I am saying? Little bit.
Yes, sir. Little bit able to understand.
Yeah, because yes, a few things are tricky. So as I said, you will be able to understand this, especially the physical layer cell ID. Okay, as I said, it is of 504 unique PCIs are there, which are grouped into 168 PCID groups. Okay, so fine. I said that this PSS is what and SSS is what. Then how we generate PSS? So I was telling about Z of 2 sequence. So if you have idea about pseudonoise sequence, then you will be able to understand what is a Z of 2 sequence. But anyhow, I am not going to discuss about what is a Z of 2 sequence and all here. Just I am saying the type of sequence used for generating PSS signal is the Z of 2 sequence. Okay, frequency domain Z of 2 sequence. So this Z of 2 sequence have the property of this constant amplitude zero autocorrelation property. Okay, so that will have a low peak to average power ratio. So PAPR will be low with that. So and this property is desirable for synchronization signals because it will be improving the coverage, and that will be an important design objective of the LTE. Okay. I think, as I said already, there are three different root sequence indices corresponds to that cell. So let me leave this. Then, yeah. So that is about the PSS. Okay, for PSS, I said it is using frequency domain Z sequence. Similar to that, for secondary synchronization signal, it uses interleaved concatenation of two-length 31 binary sequence. I think you are aware of gold sequence, what we have discussed. Okay, in case of digital communication, that M sequences, right? So that is what the type of sequences which are used for generating the secondary synchronization signal. Okay. Yeah. Okay. So as I said, this PSS, that is primary synchronization signal, is broadcast twice during every radio frame. So it will be transmitted twice during every radio frame. Means for every 10 milliseconds, it will be transmitted twice. Means for every 5 milliseconds, there will be a broadcast of this primary synchronization signal. Okay, so and both transmissions are identical. Means whatever the symbols it is occupying, means the slot, whatever the slot in that one subframe, so same set of slot it will be taking in the next subframe also. So in case of FDD and in case of TDD, I'm going to tell what are the subframes and slots this primary synchronization signal is going to occupy. Okay, so the PSS is broadcast using the central 62 subcarriers. So it uses 62 subcarriers. Okay, uh, means what I wanted to say is totally means if I take the bandwidth of 1.4 megahertz, okay, so with 10% of guard band, you just calculate what is the remaining bandwidth is available. In that, how many subcarriers you can get? Okay, maybe I think around 72 subcarriers you will get for 1.4 megahertz of bandwidth. Okay, so that 72 into 15 kilohertz, if you do, you will come to know what is the value of that bandwidth. Then plus 10% you add as a guard band, you will get the total 1.4 megahertz. Okay, so with that, what I'm saying here is this primary synchronization signal will be occupying 62 subcarriers. Okay, 62 subcarriers belonging to the last symbol of time slots 0 and 10. Means what is this? Time slot 0 and time slot 10. So time slot 0 is the what? Is the in one frame I said there will be 10 subframes, right? In that 10 subframes, right? So there will be 2 slots. Okay. So this PSS will be taking the first slot, that is slot 0, and as well as the slot 10. Okay. Hope this point is clear. And it will be occupying the 62 subcarriers. Why I'm saying central 62 subcarriers is there will be with 1.4 megahertz, I said there will be 72 subcarriers. So it is using only central 62 subcarriers, and 5 subcarriers at the top and 5 subcarriers at the bottom will not be used by this PSS. Okay, I think you will get that idea with respect to that software. I can show that. That is in case of FDD. Okay, in case of TDD, this PSS is broadcast using the same central 62 subcarriers, and at what this one, see, it is using third symbol of time slot 2 in the subframe 1. Okay, it is using third symbol of time slot 2 and the third symbol of time slot 12. That is the subframe 6. Okay, so with respect to FDD, it uses slots 0 and slot 10. You just think slot 0 comes under subframe 1 and the slot 10 comes under which subframe? So 2 slots is one subframe, right? So this slot 10 comes in the subframe of 5. Okay, yes or no? So similarly, for TDD, I said it is using third symbol of time slot 2 in subframe 1 and the third symbol of time slot 12 in the subframe 6. Okay. So that is why the subframe 1 is always a special subframe so that the PSS is sent as part of the downlink pilot time slot. That is in case of TDD. As I said, there is special subframe, right? And subframe 6 may or may not be a special subframe. That depends on uplink or downlink subframe configuration. Okay. So this is special subframe for configurations 0, 1, 2, and 6 is there. So there are different types of configurations. I will explain in detail about that. What are the different types of configurations? As of now, what you can understand is this is special subframe will be there for these configurations. That is 0, 1, 2, and 6. Okay, otherwise there will be normal downlink subframe only. Yeah, I think, yes, as I used to say, the PSS is used to detect the symbol timing, right? I said is used to achieve subframe, slot, and symbol synchronization in the time domain, and it is used in the frequency domain, right? And it is used to deduce the pointer towards one of three physical layer cell identities, that is PCI. And PCIs are organized into 168 groups of 3. So I hope now I think you will be able to get that idea. 168 groups of 3. Okay, so 168 into 3, if I do, I will be getting 504 as the unique physical layer cell IDs, I said. Okay, fine. So this PSS will identify the position of this PCI, that is a physical layer cell identity, within that group, but it will not identify the group itself. So I think 3 groups are there, right? 3 groups. That is PCIs are organized into 168 groups of 3. Okay, so it will be identifying the PCI within the group, but it will not identify the group itself. Okay, means it will not identify which group it is. Okay, it will identify the value of PCI within the group. That's all. So PSS cannot be used to achieve the radio frame synchronization. I think you should be able to get this point. So radio frame synchronization is done by using SSS, that is secondary synchronization signal. Okay, so because why I am saying PSS is not used for achieving radio frame synchronization is both the transmissions within the radio frame are identical and equally spaced in time with respect to this PSS I am talking. Okay, so I think this formula I already said. So let me say about what is this secondary synchronization signal. So the secondary synchronization signals also broadcast twice within every radio frame, similar to PSS. So it will be there next to PSS only, SSS. So the two transmissions of the triple S are different. Okay, so means two transmissions. What I said in case of PSS it is same, but in here it is different, right? So the user equipment can detect which is the first and which is the second one. So with respect to FDD and TDD, let us see what is that. In case of FDD, the secondary synchronization signal is broadcast using the central 62 subcarriers belonging to the second to last symbol of time slots 0 and 10. As I said now, next to PSS is the secondary synchronization signal. I think if that is the case, you will be able to get the clarity. In case of TDD, this secondary synchronous signal is broadcast using the central 62 subcarriers belonging to last symbol of time slot 1 that comes under subframe 0 and the last symbol of the time slot 11, so which comes under subframe 5. That means if I say it is 0 to 5, that is, or subframe 6 if I say 1 to 6. So in that sense, you don't confuse this subframe 5 or subframe 6. Means if I say yes subframe 0, then it will be subframe 5. If I say yes subframe 1, then it will be subframe 6 in that sense. So both the time slots, that is 1 and 11, are always within the normal downlink subframes. And this secondary synchronization signals are used to achieve radio frame synchronization. So this is what the use of triple S. But PSS is not used for radio frame synchronization. So what is achieved also I said, just have a look. So yeah, I think the next point is similar to the triple S. Okay. I think let me stop with this. I want to feel. Okay. Just let me show this. You'll get an idea. I will take another 2 minutes. Yeah. Fine. Yes, able to see? Hello?
Yes, sir.
Yeah, this is
Yes, sir.
how, this is how uh, what I think it is very small, what I feel. Is it so?
Can you zoom it a bit, sir, like little bit?
How do I zoom it? Yeah, is there,
Double click.
Double click. 1 minute here. Oh, if I double click, it is going back
Or
now.
sir, you can use this. There is percentage, no, sir. That 57%, like that
No, it is
small.
not PDF file. It is in the slide. It is there.
Yes, sir. Slide one only. It will increase. If you use that right hand corner,
Okay.
minus plus is there, no, sir. If you go towards plus.
Yeah. Just 1 minute. I am not able to identify.
Right hand corner, sir. Right hand corner.
1 minute. I will. Okay. Yeah. No, it is not increase. Okay. But if it is, yeah, is this fine? At least I think you are able to. Yes,
Yes,
my
sir. We
dear.
can see now.
You can see, no? Yeah, I think. Yeah, I will. Yeah. Uh, here it is written central 62 subcarriers. Okay. Yeah, this picture will be very clear if you see with respect to that software. Huh? Yeah, see, this upper 5 subcarriers will not be used. Okay. Able to see that DTX is there now. So upper 5 subcarriers will not be used. Similarly, the down 5 subcarriers will not be used. So middle 62 subcarriers have been used for this primary synchronization signal and secondary synchronization signal. Okay. So yes, able to get some idea how the picture, this resource element, how it will be. So it is complex only. Okay. It is not that easy. So let me try to make you understand. Hope you are seeing this. No? This is the secondary synchronization signal. And next one is the primary synchronization signal. In that, yeah. Okay. Okay, so let me, I think, stop with this. Better let me show you that software. So tomorrow, I think I can You all can download. Okay, I can demonstrate how to use that also, and some clarity you will get. So I was telling about that cell specific reference signal. Okay, so many things are there now. So all those things you will be able to understand with that. Okay, is that fine?
Which software, sir?
I said no. What is that I said?